This is Answer Everywhere, where we read source code. Today we're doing a series on theorem provers, or proof assistants. These are software tools that help you prove mathematical theorems. We're going to do 3 today. We're going to do Lean. We're going to start with Lean, then go to Agda and Coke. Originally, I had wanted to do them in the reverse order, and then I realized Coke is mostly written in OCaml, which I've never written before. It's the language I'm least familiar with. So this will be, I think, in reverse chronological order. I believe Lean is the newest, Agda is the second newest, and Coke is the oldest. I think possibly going to the 70s or 80s. Maybe we can look that up. And so we'll see what we can see. This will be, like my many other code reading streams, we'll be looking at these projects from the point of view of a professional software developer who's looking to contribute to these to the source code, to this as a software project. That's really different from looking at them as a user who's looking to prove mathematical theorems. Well, it's not necessarily really different. Those are actually pretty closely related, and we may see a little bit of that here. But we're not going to focus on things like how to prove things, how to use tactics, or whatever people do in the theorem proving world. We will eventually do that as part of this channel. Followers of this channel will know that I've revived the ancient religion of the Pythagoreans, and the basic way you worship in the Pythagorean religion is you try to understand the universe. And the universe includes things like you and me. So not just, like outer space and astronomy, but also psychology, neuroscience, all of the things kind of scaled down. Functional programming has been a focus of this channel since the beginning, mostly on Haskell. And the way that I'm thinking about it is that Haskell is really the closest language to the kind of functional language you get in something like a proof assistant, while also being used in production as an ordinary programming language. Now, Haskell is not used a huge amount in production, but it is deployed in a way that something like Agda or Idris is not yet. So that's kind of how this these proof assistant stuff intersects with what we've been doing. But again, I want to emphasize that today we're just really looking at the software as a developer and not as a mathematician or somebody trying to understand theorems or the universe or anything like that. This was a request by user LC, who had a lot of great requests. These are the last of the repos. There are a couple of tutorial style things which I will try to get to. I may decide that we've already covered enough of them, or that there are better resources for the tutorials I was asked to do. But this really fills out the repository requests that I've gotten. And so once we're done with that, we can kind of move on to the new regime that I mentioned before. All right. So we will time box these theorem prover explorations to 30 minutes, which I may have just said. So I'll set a timer. And let's go. So this is Lean. I believe it's from Microsoft Research. I don't know if I'm going to get in trouble for calling them theorem provers. So Lean, Agda, and Coke. I wanted to look up the timeline here. 1989 for Coke. I was a decade early. So late 80s, early 90s. Agda is when? 1999. Katerina Kokand. Is she related to Thierry? Is it even the same name? Now I must know. All right, well, maybe that's a common name. I don't know. Okay, so Agda is actually really close on the heels of Coke, and Lean is from 2013. We're looking at Lean4, which was released when? I'm not sure. But let's check it out. So we see here in the languages section that there's a good amount of C++, less than 12%, and a lot of Lean, which is a language I don't have any familiarity with, but you probably don't either, unless you program in Lean. So we'll see what we see. I imagine a lot of the stuff that's in Lean is going to be theorems or libraries of mathematical results. I know that a big part of the Lean project is to build a huge library. I suspect that a lot of that is not hosted in this GitHub repo, but they probably will want to get users started with some just basic results. So you don't, for example, have to prove what a number is or a complex number or something like that. And I wanted to look at Lean3 and see if they have the same kind of ratio of Lean to C++. No. Okay, so Lean3 is mostly C++, 74.9%. I don't know if there's a quick way to see how large the repo is in terms of file size, but it may be that Lean4 re-implemented a lot of the C++ in Lean, or it may be that the larger amount of Lean4 in the larger amount of Lean code in Lean4 comes from adding proofs. So source will obviously be important. Stage 0 is often something that people use to describe a bootstrapping thingamajiggy. That might be bootstrapping the Lean compiler. That might be stage 0 of bootstrapping the proof library. I don't know. Nix is going to be dependency and build system stuff. Nix is a what's the word? Package manager, which we've looked at the source code for. And release drafts might be documentation. We have some markdown files. Okay. So let's see what's in. So we also have script. So script has some Lean stuff like apply.lean and some stuff about diffing, change logs, gen constants, patch, LLVM. This I think is for release and like development scripts. Stage 0 has source and standard lib. I don't know which of these is more interesting. Source has C files, including lake.c and lean.c. And then what is, sorry, that's standard lib. What is source? Source has lean/server, include /lean initialize kernel. Kernel might be the kernel of the proving thingamajiggy. I'm guessing shell is like the Unix shell, and some .in files. Okay, so that's stage 0. Let's see. Kernel is C++. And I'm seeing things like for each expression equals. So that is probably going to be part of implementing the language. Lake. Lake Lean Make is the new build system and package manager for Lean4. With Lake, the package's configuration is written in Lean inside a dedicated Lake file.lean stored in the root of the packages directory. Okay, so I guess Lean is expressive enough to write its own configuration in, and they've chosen to do that. In library, we have things like class that might be implementation of classes in Lean, some more expert stuff. And in runtime, we have things like allocators, apply, debug, compact. I'm not sure what compact will be. Maybe some kind of memory compaction. I don't know what buffer is. flet, hash, etc. Okay, so this looks like runtime stuff. This looks like it's focused on execution. And then let's pull, that was all in stage 0. Let's pull out and see what's in source. We have init, which is probably not the most cool, but we also have lean, standard, cmake, include / lean, initialize. So a lot of the same directories. Lake is the build system. We also have runtime stuff in source and also shell. And we have standard.lean and lean.lean. And some build looking stuff. In init, we have mostly lean files. In source lean, we have what? Elab, that might be like elaboration. We have a linter, we have meta, which is probably related to metadata or meta information in some way. Also class.lean, declaration, declaration range. Okay, so lots of lean files. This might be on the side of language implementation, but in lean as opposed to C++. Then in standard, we have data.lean and some data. These look like containers, like hash maps, hash sets, etc. Include lean has lean H and lean GMP. I think GMP is like what, numerical numbers. GNU multi-precision library, a popular library that gives us the ability to operate with arbitrary precision numbers. Rationals and floating point numbers. Okay, so certainly things like big integers, but maybe also arbitrary precision real numbers. So I guess we probably don't really need that. And initialize, we probably don't need kernel. We may need, this is all C++. Standard.lean is just importing standard.data. That's not so interesting. Lean.lean is just imports. Okay, so we've narrowed it down a little bit, but not, I don't have a sense yet of really what is where. So let's pick on some stuff in, we want init. What is omega? Coefs is probably coefficient, linear combo, linear combination, constraint. Let's pick out a few of these. I don't know what the word omega means. I don't know if it's a code name or if it's I'm not sure. Int list. Currently, omega uses a dense representation for coefficients. Let's look up lean omega. Sounds like it might be a code name. About Lean4 omega proof. Yeah, I don't know. Okay, so we have coefficient stuff, abbrev coefs int list. I don't know what abbrev is. Presumably it's supposed to be an abbreviation. From this comment, it looks like maybe it's just a type synonym. We have abbrev toList is a thing that I guess takes a list of coefficients, and I'm guessing this means it returns a list of ints, and it's just defined to return the thing inside the coef that was passed to it. Identity, turning coefs into a list. So this is just, I guess, changing the type from coefficients into a list of int. And let's just look at another one. Dot takes x's and y's, which are coefficients. It's going to return an int. And we're going to call int list dot dot to x's, y's. And so we, I guess, learn a little bit here about the type system. So x's and y's came into the function as coefficients, which we know is really just a type synonym for list of ints. And we can still call the int list dot dot function on them. So at this level, at least, the Lean knows that it doesn't insist on like casting, for example, these somehow to official list ints. It can just treat coefs as lists of ints. Here's constrain inside of omega. A constraint consists of an optional lower and upper bound inclusive, constraining a value to a set of the form the empty set, a singleton of x, a list of x and y, I guess maybe an interval, an interval unbounded on the right, on the left, and so on. I still don't know what omega is. We might be like looking into something that's relatively small. I mean, all of that looks regular mathy so far, but I'm not sure what omega is supposed to mean. So there could be some more important place to look. Let's try core M lean. And maybe eval. And expression. Whatever hygiene is. Level, I suppose. Meta. Message. We have a parser that I guess is written in Lean. Maybe we should look at it just for fun. Replay runtime.lean. A structure, a sub expression. So this looks pretty much like compiler-y stuff, I guess. And here's the kernel. We'll come back to that. So core M lean, 534 lines, not huge. We've got some registration functions. Register built-in, option diagnostics. We have some cache. And a struct for state. I guess this is what the syntax for creating a structure or record looks like in Lean. We have some environment, a next macro scope to avoid accidental name capture. So I'm not sure what a macro is in this context. We have a name generator, a trace state, a cache, some messages, which I guess seem to be for logging, and an info tree, which is an elab.info state. We have the info tree here because we want to update it while adding attributes. All right, and we also have a context. The name of the file being compiled. Okay, so this is compiler stuff. So for example, we have the file name, some options, current, I guess, recursion depth, and so on. And I guess I don't really care so much about the compiler. Here's eval extension that gives access to the current environment and options. Okay, so I'm going to close all this stuff in source Lean. I'm guessing this is mainly compiler-y. We have messages, message data context. Just seeing if I can try to rebut my current hypothesis that this is all compiler stuff. We have message data of format with infos. Eagerly formatted text with info annotations. And I'm just scrolling through trying to see has tag. This does not returns true when the message contains a message data.tag. Okay, so all right, so I'm going to, like I said, get rid of this stuff. Here's the kernel. I guess we'll look at expression or expr rather, and expr.cpp. Should we look at inductive? I guess so. So expression.h, we've got some binder stuff and some like propositions, like whether it's the default is implicit, is strict, implicit, etc., etc. Then we have enum class literal kind, and I guess the literal kinds are nat and string, natural number and string. And then we have the class literal, which is extending public object ref. I don't know if that means that it's like a reference counted object, but we have some constructors and all of that sort of thing. We have this function kind, which you give an object star, and it's going to return static casting. It's going to return whatever cn stir tag of O, something string tag, maybe context string tag, maybe, I don't know what cn is, but we're going to look in the object, get some sort of string tag, I assume, cast it, do a static cast as a literal kind, and get that back. So this is somehow kindifying it, but I'm not sure really what the tags are yet. Similarly, we can call kind with no argument, and we get kind of raw of nothing, which I have no idea what that could possibly mean. We have some operators, like we can check if two literals are equal. What do we're still in literal? Okay. Yeah. So you can check if two literals are equal. And you can, they have an, I guess, an ordering relationship. And then we have some expressions. And these expressions are, I guess, this is like, looks like it's for, it's like a grammar for stuff. And I'm noticing that my image is all messed up. So I'm looking at expression. All the stuff up here, we're doing some stuff, creating some literals. We have a literal is either a nat or a string, it looks like. These are literal expressions. And then down here, we have some more expressions. An inductive expression seems to be what? We have bound variables. And I guess a bound variable is a bvar, and maybe we're supposed to interpret this as a type. It's a thing that takes a natural number and returns an expression. Maybe the number is like the index of the variable. If you count the variables in the thingy, then it's like the index of the variable, like when you do printing in a language like, say, Python, perhaps, something along those lines. We have fvar, which is a free variable, and we don't have a nat, so which would be consistent with that theory. It doesn't have an index to, and so we don't get a nat, we just get a name, presumably the name of the free variable, and we expressionize it. Probably there's not much we can really do other than just use the name as an expression in some sense. We have meta variables. I don't really know what they are, but maybe there's like a meta, a variable in the meta language that the logic, that there's a logical statement in the language that's implementing the thing that the thing that the variables are variables in, and it's perhaps a variable in that meta language. We have a sort, which takes a level and produces an expression. I'm guessing a sort is like a kind, just basically a way of avoiding Russell's paradox. Or maybe, let's try sort lean. I really want the word sort. Are sort, type, and kind always interchangeable? This is a question about English. I think not about math. So we have type classes. Type classes were introduced as a principled way of enabling ad hoc polymorphism. So we are probably familiar with this from Haskell. We've done a reasonable amount of Haskell. I'm not sure. Is it going to tell me what a sort is? Maybe there's a sort. We have some monad stuff. A universe sort U, a type constructor. Okay. Translating types from Lean to C. The type integers UN8, these are like the bounded standard C integers, are represented by the C types UN8 underscore T, etc. A char is represented by uint32T. Float is represented by double. enum, so on and so forth. An inductive type with a trivial structure, that is, it is none of the types described above, it is not marked as unsafe, it has a single constructor with a single parameter for relevant type. Nat is represented by lean_object star. What? Its runtime value is either a pointer to an opaque big num object, or if the lowest bit of the pointer is 1, lean is scalar. An encoded unboxed natural number, leanbox, lean unbox, a universe sort U, type constructor, ... sort U, or proposition P, type prop is irrelevant. It is either statically erased or represented as a lean object star with the runtime value lean box of 0. That doesn't tell me really what a sort is, but it's something. It's kind of like a kind, perhaps. And we have constants. Application, I guess, is an expression which takes two expressions and produces another one. Maybe like function evaluation might fall into that. I'm not really sure. We have lambda abstraction, which takes a name and binder info. So it takes a name, presumably the name or of the function. The binder info should be information about how variables are bound. The first expression might be what? The actual lambda expression. Like if the lambda is like x goes to x squared, I guess that's what that would be. And the second expression must be the thing that you're substituting in for x, like 4. And then the last thing we get is some other expression like 16. We have for all e, which is a dependent arrow. Dependent on what? I don't know. Maybe dependent on the first type, or maybe dependent on something that's not shown here. We have let expressions, literals, metadata, and projection. Projection takes a name and a natural number and an expression and produces another expression. So maybe this is like, if I have some vector like 1, 2, maybe the name is the name of the vector, like v. No, let's say our vector is 3, 9. And then that might be the index. Let's say the index is 0. If it's 0 counted, then I don't know what this is. I'm not sure. I'm going to guess this is maybe like projection from like get one of the get one of the positions in a vector, but I'm not sure. Okay, and then we have some stuff with like a enum class, expression kind. These are the things that were listed up here. And what? We have some testers. Like, is it a bvar? Is it pi? What is pi? Is pi the projection? No, pi is, so proj is projection. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pi is for all. So capital pi. Sounds good. All right, so that's some C code for Expr. Is the C++ going to be interesting at all? I'm not sure. We'll just scroll through. Probably not really. Okay. And then we have this inductive.h, which we've already seen a little bit of how they think about inductive types. Is there anything interesting? So inductive reduce rec. This looks interesting. So it's going to return an optional expr. Maybe the optional is being used kind of like nullable. So if it's not populated, then that's something has failed. We've failed to reduce, perhaps. We are templated. We are templated with the type name. This should be whitehead normal form. Type name infer. And type name is def equal. Def equal might be equal by definition. Definitionally equal is, I think, the way to say that. Let's look at Whitehead normal form. I don't remember what form that is. There must be a, come on. This is Wikipedia. Oh. Am I misremembering that this is a thing? Oops. Let's try this one more thing. One more time. Right, Whitehead normal form. Yeah, then what is it? Weakhead normal form. Well, that's different. I was misremembering it. Okay, so weakhead normal form. The definition below is flawed. It is in contradiction with the definition saying that weakhead normal form is either head normal form or the term is an abstraction. The notion has been introduced by Simon Peyton Jones. Reduction to the function, the head, have been applied, but not all reductions to the parameter have been applied. This result is obtained from applying lazy evaluation. So weak head normal form of lambda x dot y of z is false. So I guess WHNF is testing, I guess, whether it's in weak head normal form. So if there's all reductions to the function, to the head have been applied, not all to the parameter. I'm not sure what reductions there are to the parameter here. The parameter is z, right? Or is y counted? I'm not sure. And some normal form. What is regular head normal form? Yeah, so this is lambda expression stuff. It's probably worth looking at, but I don't know this stuff now, and we're not gonna, with 30 minutes, I don't think it would be fair to Lean to go too deeply into it. Okay, so yeah, so we have inductive reduce rec, and we're gonna get app function. So we're gonna pass in some environment, the expression, an expression, presumably the expression we're trying to reduce, the something about WHNF const being ANDed with the lowercase WHNF, this infer const and infer type is def equal const, but this is def equal. And we're going to get app function of E, maybe get, what is get app function? It might be like looking into an expression and looking for the function to be applied. It's in expr of h, expr.h, I mean, rather. So given CE of the form blah, 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 f of a1, blah, 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 an, return, I guess C is maybe an instruction to the documentation engine. So it's going to ask to return f when you ask it to get app function. If E is not an application, then return E. So I don't know if this means that there's only one application or if it returns the first, but I guess we're getting the function being applied. So we have the rec function. We check if it's constant, in which case, if it is, we return none expr. Then if we're done here, it's non-constant, or rather, no, we're checking if it's non-constant. I'm not sure why. Maybe there's a meaning of constant that I'm not seeing. But if we're down here, then I guess the function is constant. The rec fn is constant. I'm guessing it, well, probably doesn't mean that it's like a constant function. But we're going to look in the environment for the constant name of the rec function. And we'll get constant info. And if we don't have rec info, or if it's not a recursor, then we'll return none-expr. None-expr must be the failure mode. Then we'll create a buffer of expressions for the rec args, and we'll call get app args on E, which was the expression we passed in. And we'll ask the rec info to give us recursor values, recursor val, probably value, something like that. And then we'll ask the rec val to get the major index. And if the major index is bigger than or equal to the size of the arguments, then the major premise is missing. Otherwise, we get the major premise from the major index, etc. And we go on and on. Okay, so that might be like relatively fundamental. That looks like some sort of reduction argument, some sort of reduction function. I'm curious about is constant now. It calls is const. Maybe the question is like whether the is const. Maybe it means it's const in the C++ sense that like the function, it's like once it's been named, the function can't be changed. Like if it's the sign function, it stays the sign function rather than the function being like the constant function that always returns 5. Okay, so that's some of the C++ stuff. I'd like to see if we can see some of the mathematical, some of the mathematics looks like. So let's try, what's a mathematical thing that, I doubt there's any calculus in here. You get some licensing info. How about Cauchy? Okay. How about rational? Here we go. rat.lean. And this is in lean/data/rat.lean. Rational numbers for implementing decision procedures. You should not confuse them with the mathlib rational numbers. Okay, so what is lean mathlib? Is that the library of math, or is this something else? Okay, so mathlib seems to be the mathematics library. We have 12 minutes left. I usually don't jump between repos. This is the Lean Prover community. So this is, I guess, the community. So this organization is controlled by the Lean community as opposed to this organization, which is probably controlled by Microsoft or whoever controls Lean now. I have a feeling that the math is sufficiently interesting. Hello, Isaac Home. First time here. Welcome, welcome. I have a feeling that this is sufficiently interesting that we should at least look at a little bit of the math. Counterexamples are always fun, although I don't know if this is like how, using a counterexample. Longest poll. That might be an example directory. So, okay, so we have algebra, algebraic geometry, combinatorics. So let's just pop a few of these open. Analysis, category theory. Computability. Deprecated is presumably things that are actually deprecated and not things that study the mathematics of deprecation. Information theory. Logic. These are all cool. These are all a good time. Ring theory said, what? How is ring theory? I guess ring theory has a sufficiently different flavor from algebra. Topology is always fun because I feel like topology is hard to implement in computers compared to something like algebra. In algebra, I'll just kind of look through some of these. So car P, presumably characteristic polynomial, divisibility, Euclidean domain, field, group. Presumably there's some ring in here. Yeah, square, free, star, tropical. Okay. So we'll look at some of these files too. I just want to get a feel for what topics are covered so that we can pick one that's cool. Algebraic geometry has elliptic curves. I guess in theory you could try to prove some properties of cryptographic elliptic curves. I don't know if anyone has done that using Lean. Properties is presumably just some stuff about properties, gluing, limits, scheme, spec, stalk, structure sheaf. I'm curious just how long spec is. 432 lines, not much. That's kind of cool. Here's algebraic topology. You have things like a fundamental groupoid, which is always fun. Simplicial category, simplicial set. The check nerve, more complex. Nerve, simplex category. I don't know. It would be cool. So let's take quasi category. This is what algebraic topology. In an ideal world, this quasi category would kind of work nicely with the stuff that's in category theory. I don't know how to check that. We are importing the namespace is S set, and we're opening category and some category theory and simplicial. So I'm guessing we do use some category stuff too. So the class quasi category S is an S set. We have some proposition where S set is simplicial set, and here we go. This is actually describing what we're doing. A simplicial set S is a quasi-category if it satisfies the following Horn-filling condition. For every natural number n and index between 0 and little n, every map of simplicial sets, sigma sub smiley face, something, mapping from the wedge of n comma I to S can be extended to a map sigma to the simplicity thing of n to S. Okay, so I think what this is saying now is that this is the definition. So quasi-category is the S is of type simplicial set. It's an S set. And this prop where is, I guess, part of the definition. It satisfies this Horn filling condition. And we have for all, and I guess some Unicode, because we get Blackboard bold. N, which is of type N must be the natural numbers. We have I of type fin n plus 3. I don't know what that means, such that this thing, this wedge n plus 2, I to S, etc. And then where does this close? This, I believe, is opening the curly brace opening a set. Although maybe I'm not reading it correctly. Oh, is that the close? I thought this was a such that. Okay, never mind. I was misreading the font here. Okay, so this is not like a clause that refines that refines this. This is just a separate statement of some sort. But anyway, what I was trying to understand is that this is kind of like a constructor. It's a constructor where you have like a logical proposition that refines what kind of S set we're allowing to be a quasi category. And then we have this Horn filling lemma, and I guess these are like the assumptions. And what are we? I can't tell like syntactically what we're trying to prove. I don't know if this is part of the proof or part of the assumptions. Presumably down here, this is part of what we're trying to prove. And then we do like a case analysis. This looks pretty similar to how you might program in Haskell. You're going to You have cases n using that cases aux on. I don't know what cases aux on is. Hang on. And we have this other case analysis. So it seems like these are both cases. Yeah, I'm not sure. Or these seem to be both case things on n, and I'm not sure if they are like anded together or ored together or what. But that's what that's what some proof looks like. Here's analysis. We have analytic asymptotics calculus, functional spaces, inner product spaces, norm spaces, ODEs, and so on and so forth. Category theory. Just kind of scroll through monoidal, pi, Galois, functored, fiber categories. Yeah, there's lots of stuff here. Computability. A few. DFA, encoding, Ackermann. Okay. So that's good. This is all good. Mildly curious about ergodic. Add circle conservative ergodic function. Okay. So this is that's some of the math. So let's close MathLib. And how much time do we have? 4 minutes. Let's see if we can find some stuff about proofs. Like how are proofs implemented? I guess maybe the type checking algorithm would be a big part of that. Okay, so we'll look quickly at these 3 files, I guess. These 5 or 6 files, I guess. Oh, this is counterexamples. Direct sum is internal, cyclomatic, map, floor, Phillips. Yeah, I think these are like famous counterexamples to known. You can get these books like counterexamples and analysis and so on. I think those are like famous counterexamples to a curve that is everywhere continuous but isn't differentiable and stuff like that. All right, so here's the type checker, which is in source kernel, and this is the header. We have a type checker as a class. The Lean type checker. It can also be used to infer types, check whether a type A is convertible to a type B, etc. And it has some state and an environment, a name generator, an inference cache, an expr map of expressions, which is the weak head normal form core, and another expr map of expressions, which is weak head normal form not core, an equiv manager, maybe that's for managing equivalences, and an expr pair set, which is M failure. So that's some state, and it's, I guess, mostly looks like caches for handling presumably the harder parts of inference. We also have some functions like ensure sort core, ensure pi core, which sounds like a music genre. Infer constant, infer pi, infer app is def EQ, etc. Try string lit expansion core. So this looks like ensure fun. This looks to me like people who have a good who are experienced writing type checkers, and it's very complete. There's lots of helper functions. Everything is organized really well, but it's not slickly elegant, which kind of is a hint to me that there's perhaps a focus on it being nice to work with from a developer point of view, and also probably performance. Here's types.c in meta tactic grind types. I don't know what grind is. This is a .c file. Maybe we can, is there a header? Let's look at grindcore, which is definitely a music genre. We're exporting some stuff. And I'm not really sure how to look at this. Is this generated code? Lean compiler output, yes. So this is some compiler output of, I guess, maybe we compile Lean programs to C. I don't know if that's how it works. But we have like recognizable symbols like x_7 is of type UN8. And we're going to call Lean Inc on x_1. And then we're going to call 1 or maybe L Lean. Is that a 1 or an L? I think it's L. Yeah, so wherever we were calling L Lean expression is false, etc. Here's abstract nested proofs. This is again compiler output. So these must have come from like a Lean file. Here's typechecker.cpp. And we have a bunch of static stuff like kernel fresh, nat sub, nat land. I'm not sure what LOR is, but we have nat XOR. And here's a function, typechecker ensure sort core. Make sure E is a sort and return the corresponding sort. If E is not a sort, then the WHNF procedure is invoked. I don't know if that means that WHNF produces a sort, but ensure sort core says if it is a sort, then we just return E. Otherwise, we call WHNF of E and get a new E. And we're using auto. It's not obvious to me what this produces. I'm not really sure what type new E is. And if the new E is a sort, we return new E. Otherwise, we throw an exception. So whatever WHNF is doing, it's presumably trying to turn it into weak head normal form. And that, I guess, things that are in weak head normal form are most likely to be sorts. Or maybe the idea is just that like the thing you pass in is supposed to be a sort. If we're here, maybe we just can't tell. And then if we're here, we know enough that we can tell that it's not a sort. And so you messed up by calling this function on it or something. All right. So that's just a little bit of Lean where our 30 minutes are up. So let's move on to Agda.